In this video, I will explain narrow bandpass filter analysis. This is the narrow bandpass filter diagram. The narrow bandpass filter uses only one opamp. This is only one opamp as against two by wide bandpass filter. In wide bandpass filter, we use two opamps. In narrow bandpass filter, use only one opamp. It has following features. It has two feedback paths. This is the feedback path 1 and feedback path 2. Two feedback paths. The op-amp is in the inverting configuration. The op-amp is in inverting configuration means input voltage is connected to Vin is connected to inverting terminal of the op-amp. That is the reason the op-amp is in the inverting configuration. Due to the two feedback paths, it is called multiple feedback filter. This is the feedback path 1, and feedback path 2. Due to these two feedback paths, this filter, narrow band pass filter, is also called as a multiple feedback filter. Multiple feedback filter. This is the description of that narrow band pass filter. Instead of two op-amps, in this filter we use only one op-amp. This is called as multiple feedback filter. Multiple two feedback paths are used here. The op-amp is in inverting configuration. That means Vin is connected to inverting terminal of the op-amp. The important parameters of the narrow band pass filter are FL, FH, center frequency FC. The gain at the center frequency AF and the quality factor Q. These are some important parameters related to narrow band pass filter. Later we will see the in derivations. For simplifying the calculation, choose C1 is equal to C2 is equal to C. Two capacitors are used here. C1, C2. Therefore, C1 is equal to C2 is equal to C. By using after a derivation, we will get R1, R2, and R3 values. R1, R2, and R3 values. Later, we will see the derivations of this R1, R2, and R3. And AF is equal to the gain at center frequency. Gain at FC is equal to AF. That is equal to R3 by 2R1. The gain AF must satisfy the equation. This is the AF less than 2Q square. Otherwise, R2 is negative. Resistance R2 is negative otherwise. AF less than 2Q square. Changing the center frequency FC. FC is the original frequency. FC dash is the new center frequency. The new center frequency can be achieved by changing the only resistance R2. The new value of resistance, say R2, can be obtained. R2 dash is equal to old value of that resistance R2 into FC, old cutoff frequency, original cutoff frequency by FC dash, new cutoff frequency whole square. This is an important advantage of multiple feedback circuit, that FC can be changed without changing the AF or bandwidth. Center frequency of that narrow band pass filter can change it without changing the gain and bandwidth of the narrow band pass filter. This is the gain versus frequency. This one is FC. The bandwidth is very narrow. Selectivity is equal to Q is equal to FC by bandwidth. If the Q is very high, Q greater than 10 for a narrow band pass filter, bandwidth is very less. This is the bandwidth is very less. At FC, this characteristic curve has some peak. This is the peak value. That peak value corresponding to that gain is AF, FL and FH. This is the frequency response. Now I will derive R1, R2, R3 and transfer function of this band pass, narrow band pass filter. Again, draw the circuit diagram here. This one minus plus here V in R1. Here in C1 means 1 by S C1. Here R2. Here R2. RL V naught. This one is R3. This is a multiple feedback filter. Another one. This one is 1 by SC2. This is the compensating resistance is also there. This is the actual circuit diagram. 1 by SC2 capacitor reactance is 1 by SC2, 1 by SC1, R1, R2. This one is R3, R3, R3 here. This one is here some compensating resistance. This one is R3, RL. V in is connected to ground. This point is 1. The voltage at point, the junction point 1 is V1. Here non-inverting terminal, that means plus terminal is connected to ground. Here the voltage is 0 due to virtual ground concept. At this point, the voltage is 0. Here also 0 voltage and 0 voltage. Apply nodal analysis at these 2 points. Apply nodal analysis. Apply nodal analysis at point 1 or junction 1. The node that is voltage at 1 is V1. V1 into the admittances connected to that V1 are 1 by R1 plus 1 by R2 plus 1 by SC1 plus 1 by SC2. These are the branches. These are the branches connected to. This is the branch. This one is branch. This one is another branch. 4 branches are connected to node V1. Therefore, V1 is equal to consider admittances of that branches. V1 into 1 by R1 plus 1 by R2 plus 1 by SC1, that means SC1 plus 1 by SC2, that is SC2, minus adjacent node voltage. Adjacent node voltages are V in V naught, V in V naught, minus V in by R2. The resistance between not R2 here, R1. This one is R1. The resistance V1 between V1 and the adjacent node voltage V in is R1 minus the impedance 1 by SC2 connected between V1 and adjacent node voltage V naught is 1 by SC2. That means V naught S C2 is equal to 0. This is the equation 1. This is equation 1. Apply nodal analysis at this point 0. 0. That means here 0 into 1, 0 by R3, 0 by 1 by 1 by SC1. 0 into apply nodal analysis at the inverting terminal of the op-amp, at the inverting terminal, terminal of the op-amp. That is 0. Here 0 into 1 by SC1 means SC1 plus 1 by R3 minus adjacent node voltage is here V1 by 1 by SC1. That means V1 SC1 minus here V0 by R3. V0 by R3 is equal to 0. Therefore, from this equation, minus V0 by R3 is equal to V1 SC1. Therefore, V1 is equal to minus V0 by R3 SC1. This is the equation number 2. Consider equation 1. Consider equation 1. Equation 1. V1 into 1 by R1 plus 1 by R2 plus SC2 plus SC1 minus V in by R1 minus V0 plus C2 is equal to 0. Take LCM. Consider entire expression. That is equal to here R1, R2, V1, R1 cancel, R2 is cancel, R1, yes, R1, R2 into C2, R1, R2 into C2 plus SC1, R1, R2, bracket close, minus here R1 is there, V in R2, V in R2 minus V0 SC2 SC2 R1 R2 is equal to 0. Therefore, V1 into R1 plus R2 yes sir, C1 R1 R2 plus S C2 R1 R2 minus not here minus V0 S C2 R1 R2 is equal to V in R2. Here V0 SC2 R1 R2. V0 SC2 R1 R2. V in into R2. But V1 is equal to, from second equation, V1 is equal to minus V0 by, this is the second equation, minus V0 by R3 SC1. Substitute V1 here, minus V0 by minus V0. The entire term is, let it be Y. Minus V0 by S R3 C1. Minus V0 by S R3 C1 into Y minus V0 SC2 R1 R2 is equal to V in R2, V in R2 minus V naught Y minus V naught minus V naught S square R1, R2, R3, C1, C2, V in, multiply this term R2, S, R2, R3, C1. Yes, R2, R3, C1. Common term is minus minus V naught Y minus V naught Y minus Y plus, because V naught is common term, Y plus S square R1, R2, R3, C1, C2 is equal to V in S R2, R3, C1. Substitute Y in that equation. Minus V naught Y is equal to R1 plus R2 SC1 R1 R2 plus SC2 R1 R2 plus S square R1 R2 R3 C1 C2 is equal to V in S R2 R3 C1. Find out V naught by V in, that is gain of the filter, that is minus S R2 S R2 R3 C1 by S square R1 R2 R3 C1 C2 plus SC1 R1 R2 plus SC2 R1 R2 plus R1 plus R2. Common term here is minus S R2 R3 by C1 by, here the entire term is a common factor R1 R2 R3 C1 C2 by S square plus S C1 R1 R2 by R1 R2 R3 C1 C2 plus SC2 R1 R2 by R1 R2 R3 C1 C2 plus R1 by R1 R2 R3 C1 C2 plus R2 by R1 R2 R3 C1 C2. Here R2 R2 cancel, R3 cancel, C1 is also cancel. Therefore, finally minus S by the remaining terms are R1 C2 by S square plus here R1 R2 is cancelled, C1 is also cancelled, S by R3 into 1 by C2. Here R1 R2 is cancelled. C2 is cancelled. Plus S by R3 1 by C1 1 by C1. Here R1 and R1 is cancelled. R1 and R1 is cancelled. The remaining term is 1 by, here R2 is cancelled. Here here R3 C1 C2. R3 C1 C2 is in both the cases R3 C1 C2 is the common term, that is in the 1 by R2 plus 1 by R1. Therefore final expression is here, gain A is equal to minus S by R1 C2 by S square. S by R3 is the common term, 1 by C1 plus 1 by C2, 1 by R3 C1 C2, 1 by R2 plus 1 by R1. For simplicity, to simplify design calculation, C1 is equal to C2 is equal to C. To simplify design calculations, C1 is equal to C2 is equal to C. Therefore, A is equal to minus S by R1 into C by S square plus S by R3, 1 by C plus 1 by C, 1 by R3, C1 into C2 is equal to CC, that is C square into 1 by R2 plus 1 by R1. Therefore, A is equal to minus S by R1 into C by S square 2S by C R3 plus 1 by R3 square 1 by R1 plus 1 by R2. A is equal to, compare this equation with the general equation. A is equal to A naught. That is gain of that filter is given by AF. AF omega naught by Q S square plus omega naught by Q S omega naught square. Because this filter has a tuned circuit characteristics, some central frequency, that is FC. Therefore, omega naught is equal to 2 pi FC. Central frequency. Selectivity depends on quality factor of the filter. These are the two parameters which are related. AF is the gain of that filter. Narrow bandpass filter. Compare these two equations, this equation and this equation. Therefore, here negative sign indicates the op amp is in inverting mode. 180 degrees phase shift between input and output. Here compare this one. AF into omega naught by Q is equal to 1 by R1 into C. Compare this one and this one. Next. Omega naught by Q Omega naught by Q is 2 by CR3. 2 by R3C. This is the equation 1. This one is equation 2. Omega naught square is equal to omega naught square is equal to 1 by R3. This one 1 by R3 C square 1 by R3 C square into 1 by R1 plus 1 by R2. This is the equation number 3. From equation number 1, calculate a R1 value. From 1, R1 is equal to 1 by C AF omega naught by Q, that is equal to Q by C AF omega naught. Q by C AF omega naught. This is the R1 value. See, already for simplified design calculation, C1 is equal to C2 is equal to C. At the beginning, I declared C1 is equal to C2 is equal to C. And from second equation, R3 is equal to here 2 by C into W naught by Q. That is equal to 2Q by C W naught, 2Q by C, 2 pi FC, 2 to cancel. Therefore, Q by pi FC into C. This one is R3. Now calculate R2 from third equation. From third equation, omega naught square R3C square. Omega naught square R3C square is equal to 1 by R1 plus 1 by R2. 1 by R1 plus 1 by R2. Calculate R2. Therefore, 1 by R2 is equal to 1 by R2 is equal to omega naught square R3C square. R3C square minus 1 by R1. Omega naught square R3C square minus 1 by, here 1 by R1 is, here R1 value is Q by CAF omega naught. Q by CAF omega naught. Q by CAF omega naught. That is equal to R2 is equal to reverse 1 by omega naught square R3 C square minus CAF omega naught by Q. Omega naught by Q. Q LCM, therefore Q by omega naught square R3 C square Q minus CAF omega naught. CAF omega naught. That is equal to Q by omega naught square C square Q. But R3 is equal to, we know that R3 value is Q by pi FCC. Q by pi FC into C minus CAF omega naught that is equal to Q by omega naught square c square q square. Here numerator and denominator is multiplied with 2. That is equal to 2 by 2 pi fc is omega naught c minus c af omega naught. Here c is cancelled. Omega naught is cancelled. Finally, q by omega naught c, here some omega naught c is the common term. Omega naught c 2q square minus af, 2q square minus af. This is the R3 value. Therefore, R3 is equal to, final R3 is equal to q by omega naught 2 pi fc into c 2q square minus af. This is the R3 value. R1 is equal to already derived expression. We know that R1 is equal to q by a omega naught c. R3 is equal to q by pi fc into c. This one is R3. This one is R2. This one is R2. This one is R2. R1 is equal to q by a 2 pi fc into c. R3 is equal to q by pi fc into c. From this expression, fc is equal to q by a 2 pi r1 into c. From this also, fc is equal to q by pi r3 into c. Equating these two, q by a 2 pi r1 into c is equal to q by pi r3 into c. Q cancel, pi cancel, c cancel. Therefore, the gain at cutoff frequency fc is af is equal to the gain at cutoff, or the gain at center frequency, not cutoff, center frequency fc is here af 2r1 is equal to r3. Therefore, af is equal to r3 by 2r1. af is equal to r3 by 2r1. Next, cutoff frequency fc changes, but bandwidth and quality factors are equal, are not changed. Here R3 is equal to q by 2 pi fc into c 2q square minus af, but R2 must be positive. Therefore, af less than 2q square. af less than 2q square is also very, very important. This is the gain at center frequency fc is af is equal to r3 by 2r1. The gain a, however, must satisfy the condition af less than 2q square. af is equal to r3 by 2r1 less than 2q square. R3 less than 4r1 q square. 4r1 q square. Therefore, R3 by R1 ratio is less than 4q square. 4q square. Next one, that bandwidth is a constant one, and center frequency changes. Therefore, need to calculate some R2 and R2 dash. Here in this analysis, changing the center frequency. Let Fc is the original frequency and Fc dash is the new center frequency. The new center frequency can be achieved by changing the resistance R2 only. The new value of resistance say R2 dash can be obtained as R2 dash is equal to R2 into Fc by F dash C whole square. The new center frequency can be achieved by changing the resistance R2 only. Now we will see that one. Only changing the resistance value, we will get the new center frequency. Consider R2 resistance. R2 is Q by 2 pi FCC. R2 is equal to Q by 2 pi Fc into C 2Q square minus AF. But 2Q square AF less than 2Q square. Therefore, R2 is equal to Q by 2 pi Fc C 2Q square only. QQ cancel. Therefore, R2 is equal to 1 by 4 pi Fc C into Q. But Q is equal to, we know that Q equality factor Q is equal to Fc by bandwidth. 4 pi Fc into C bandwidth Fc by bandwidth. Therefore, R2 is equal to bandwidth by 4 pi C Fc square. Bandwidth is fixed one and calculate a new center frequency Fc dash. Therefore, R2 dash is equal to bandwidth is fixed. 4 pi is also fixed. C is initially designed. Fc F dash C whole square. Ratio of these two R2 by R2 dash is equal to bandwidth by 4 pi C Fc square into 4 pi C Fc dash square by bandwidth. Bandwidth cancel. 4 pi C is cancel. Therefore, R2 dash is equal to R2 into R2 dash is equal to R2 into Fc by Fc dash whole square. The new cutoff frequency, new center frequency Fc dash can be easily calculated just changing the resistance value. This is the total analysis of the narrow bandpass filter. With this, the total derivations are completed.